Right now, over 24,000 locomotives are moving across America. They haul everything from coal to cars to the packages sitting on your doorstep. And every single one of them falls into one of four categories. We're going to break down each type, starting with the machines that built this country and ending with technology that might change railroads forever. So, here's the first type, and it's the one that started everything. Type 1, steam locomotives. Steam locomotives ran American railroads for over 100 years. The basic idea is simple. You burn fuel, usually coal or wood, to heat water inside a boiler. That water turns into steam, and the pressure from the steam pushes pistons back and forth. Those pistons connect to the wheels through metal rods, and that's what makes the locomotive move. The first one to operate the United States was the Stourbridge Lion back in 1829. It came from England and only ran for a short time because it was too heavy and damaged the tracks. But it proved that steam power could work here. A year later, Peter Cooper built a small engine called the Tom Thumb. It raced against a horse, and even though it lost that race because of a mechanical problem, people saw the potential. That same year, the best friend of Charleston became the first American-built locomotive to pull passengers on a regular schedule. It worked great until 1831 when a worker got annoyed by the sound of the steam escaping and held down the safety valve. The boiler exploded. Lessons learned the hard way. By the mid-1800s, steam locomotives were everywhere. The 440 American type became the standard. That number tells you how the wheels are arranged. 4 small wheels in front for steering, 4 large driving wheels in the middle for power, and 0 wheels in the back. This classification system is called the White notation, and railroaders still use it today to describe steam engines. About 25,000 of these 440 locomotives were built, and they can handle curved tracks really well, which made them perfect for the railroads spreading across the country. When the Transcontinental Railroad was completed in 1869, steam locomotives like Central Pacific No. 60 and Union Pacific No. 119 did the work. These machines burned wood and coal and could pull heavy loads over long distances. As trains got heavier and railroads needed more power, the designs grew more complex. The 280 consolidation had 8 driving wheels for better pulling power. The 462 Pacific type could reach high speeds for passenger trains, and the 484 Northern had a massive firebox that let it run longer without stopping. The biggest steam locomotives ever built came from Union Pacific. The big boy, officially designated 4884, weighed over 1 million pounds and produced 6,290 horsepower. Only 25 were made, and they were designed specifically to haul freight over the mountains between Wyoming and Utah. One of them, number 4014, was restored in 2019 and still runs on special occasions. Seeing it in person is something else entirely. There's another category of steam locomotives that most people never hear about, the geared types. Regular steam engines work great on flat, well-built tracks, but logging companies and mining operations needed something different. Their tracks were temporary, often uneven, and they went up steep mountain grades. So engineers designed locomotives where the steam power went through a series of gears instead of directly to the wheels. The Shay was the most popular. Ephraim Shay patented in 1880, and the Lima Locomotive Works built around 2,770 of them. Cylinders sat vertically on one side of the engine, and they powered a drive shaft that ran all the wheels through gears. This setup let the Shay crawl up grades as steep as 8% while staying stable on rough, uneven rails. The Climax and Heisler were similar designs with different engineering approaches. The Climax had angled cylinders that drove a central transmission, while the Heisler used a V-shaped engine like you would find in a car. About 4,500 geared locomotives were built in total, and you can still see some of them running at places like Cass Scenic Railroad in West Virginia. Steam had one major problem, though. It was inefficient. Only about 10 to 20% of the energy from burning coal actually made it to the wheels. The rest went up the smokestack as heat. Steam locomotives also needed constant maintenance, lots of workers to keep them running, and they had to stop frequently for water and fuel. By the 1930s, railroad companies were looking for something better. That brings us to the second type, and this is the one that dominates American railroads today. Type 2, diesel locomotives. Diesel locomotives took over because they solved almost every problem that steam had. The transition happened fast, and In 1939, Locomotive Corporation put together a demonstration unit called the FT. It traveled to 35 states and showed railroad executives what diesel power could do. Within 20 years, steam was basically gone from American main lines. The last regular steam operations ended around 1960. The way a diesel locomotive works is different from what you might expect. Most of them are actually diesel-electric hybrids. The diesel engine burns fuel to spin a generator, and that generator produces electricity. The electricity then powers electric motors attached to the wheels. This setup gives you the best of both worlds. Diesel engines are efficient and reliable, and electric motors provide smooth, controllable power at any speed. There are a few variations. Diesel mechanical locomotives use a transmission like a truck, but these are rare in the United States because they can't handle the heavy loads that American railroads need. Diesel hydraulic locomotives use fluid to transfer power, and some European railroads use them, but they never get caught on here. Diesel electric is the American standard. The classification system for diesel locomotives is different from steam. Instead of counting wheels, we count axles and whether they're powered or not. The AAR wheel arrangement uses letters, where A means one powered axle, B means 2, and C means 3. The locomotive classified as CC has 2 trucks with 3 powered axles each, for a total of 6 powered axles and 12 wheels. Most heavy freight locomotives in the United States are CC types. The 2 major manufacturers have been trading the lead for decades. Electromotive Division, or EMD, dominated the early diesel era with models like the GP9 and SD42 and the F7. The SD42 was especially successful. EMD built over 3,900 of them starting in 1972, and many are still running on short-line railroads today. These locomotives produce about 3,000 horsepower and become famous for their reliability. General Electric entered the locomotive business and eventually took the lead in the 1980s. Their Evolution series, including models like the ES44AC and ET44AH, became the new standard for Class I railroads. These modern units produce around 4,400 horsepower and meet strict emission standards called Tier 4. GE's Locomotive Division is now part of Wabtec, which continues to build and service these machines. Switchers are a different category within diesel locomotives. These are smaller units designed for railroad yards where they push and pull cars into different tracks to assemble trains. Models like the EMD SW1200 have about 1,200 horsepower, which is plenty for moving a few cars at slow speeds. Road switchers like the GP38-2 can handle both yard work and mainline duties, making them popular with regional and short-line railroads. There's also something called a slug, which is basically a locomotive without an engine. It has traction motors, but it gets its electrical power from another locomotive through a cable. Slugs work in yards where you need extra pulling power at low speeds, but you don't want to pay for another complete diesel engine. Modern diesel locomotives can move a ton of freight about 500 miles on a single gallon of fuel. That efficiency, combined with the ability to link multiple units together under one control system, makes them perfect for the massive freight trains that cross this country every day. Some trains are over 2 miles long and weigh tens of thousands of tons. The locomotives at the front and sometimes in the middle and rear work together through a system called multiple unit control to keep everything moving. The third type of locomotive solves the emissions problem entirely, but it comes with a major catch. Type 3 electric locomotives. Electric locomotives draw power from an external source, either overhead wires or a third rail alongside the track. They don't burn any fuel on board, which means zero emissions at the point of use. The electricity comes from the power grid, so the actual environmental impact depends on how that electricity is generated. But from the railroad's perspective, electric locomotives are cleaner, quieter, and often more powerful than their diesel counterparts. The efficiency numbers are impressive. Electric locomotives can convert up to 90% of the electrical energy they receive into motion. Compare that to steam's 10 to 20% or diesel's 30 to 40%. Electric motors also produce maximum torque at zero speed, which means they accelerate faster and can handle steep grades more easily. The Baltimore and Ohio Railroad pioneered electric traction in 1895. They electrified a tunnel in Baltimore where steam locomotives were causing problems with smoke and fumes. The success of that project led other railroads to electrify portions of their networks, especially in urban areas and through tunnels. New York Central electrified its terminal approaches into Manhattan starting in 1906, and commuter railroads around major cities followed. The most famous American electric locomotive is probably the GG1. The Pennsylvania Railroad introduced it in 1934, and it remained in service for nearly 50 years. The GG1 was a streamlined machine that could reach 100 miles per hour while producing 4,620 horsepower. Its distinctive design, created with input from industrial designer Raymond Loewy, made it an icon of American railroading. Several GG1 locomotives are preserved in museums today. The Milwaukee Road operated the longest electrified main line in North America, covering 656 miles through the mountains of Montana, Idaho, and Washington. Their box cab locomotives and later streamlined units handled freight and passenger trains through some of the most difficult terrain on the continent. But the infrastructure was expensive to maintain, and the railroad eventually tore down the overhead wires in the 1970s. Today, electric locomotives in the United States are mostly limited to the Northeast corridor between Washington, D.C. and Boston. Amtrak operates Siemens ACS 64 locomotives that can reach 125 miles per hour and produce 6,400 horsepower. These modern units are nicknamed City Sprinters, and they handle most of the regional and long-distance passenger trains in that corridor. Commuter railroads like NJ Transit and SEPTA also run electric locomotives on their lines. The problem with electric locomotives is infrastructure cost. Electrifying a railroad requires installing overhead catenary wire or third rail along the entire route, plus substations to convert and distribute power. The initial investment is enormous, which is why less than 1% of American railroad track is electrified. For freight railroads operating over tens of thousands of miles, the economics have never worked out. That brings us to the fourth type. This is where things get interesting for the future. Type 4, hybrid and alternative fuel locomotives. Hybrid and alternative fuel locomotives are being developed to reduce emissions without requiring full electrification. These machines combine different technologies to get the benefits of each while avoiding their drawbacks. Battery electric locomotives store energy in large battery packs and use electric motors for propulsion. They produce zero emissions and can be recharged from the grid or from other locomotives. U.S. Steel started using one at their Pennsylvania plant in 2023, and it saves about 40,000 gallons of diesel fuel every year. The limitation is range. Current battery technology cannot store enough energy for a locomotive to cross the country, so these units work best in switching yards and for short-haul operations where they can recharge frequently. Hybrid locomotives combine diesel engines with battery packs or capacitors that capture energy from braking. When a train slows down, the motor works in reverse as generators, turning that motion back into electricity that gets stored for later use. This regenerative braking can reduce fuel consumption by 50 to 80% in yard operations, where locomotives start and stop constantly. Some railroads have converted older switchers to genset configurations, where multiple small diesel engines replace one large one. The small engines can be turned on and off as needed, which saves fuel when full power is not required. Hydrogen fuel cell locomotives are the newest technology being tested. A fuel cell combines hydrogen with oxygen to produce electricity. The only byproduct is water. No carbon dioxide, no particulates, no pollution. Alstom brought their Coradia Island hydrogen train to the United States for testing in 2023, and American manufacturers are developing their own versions. Wabtec has stated publicly that hydrogen is the locomotive fuel of the future. The challenges are significant, though. Hydrogen has to be produced, stored, and distributed, which requires entirely new infrastructure. The current production methods for hydrogen are energy intensive, and most commercial hydrogen still comes from natural gas, which produces carbon dioxide. Green hydrogen made from renewable electricity through electrolysis solves that problem but remains expensive. Siemens is launching a new battery locomotive called the Charger B Plus AC in 2025. It can run on battery power where there are no overhead wires and switch to electric power where catenary exists. This dual-mode approach might be the bridge technology that lets railroads gradually electrify their networks without having to do it all at once. Industry analysts project that demand for battery electric and hydrogen locomotives will grow significantly through 2043. The Federal Railroad Administration has studied these technologies and sees them as a pathway toward eventual full electrification of freight rail. The economics are shifting as battery costs come down and emissions regulations get stricter. Union Pacific and other major railroads are already testing battery-powered locomotives in their yards. The early results show fuel savings and reduced maintenance costs. When you multiply those savings across thousands of locomotives operating for decades, the numbers start to make sense even with higher upfront costs. The transition will take time. Diesel locomotives can last 40 years or more with proper maintenance, so the existing fleet will not disappear overnight. What we are seeing is the beginning of a gradual shift, similar to what happened when diesel replaced steam in the 1940s and 1950s. That transition took about 20 years. This one might take longer because the infrastructure requirements are more complex. So, those are the four main types. Steam built the railroads that connected this country. Diesel made them profitable and efficient. Electric proved that zero emissions are possible with the right infrastructure. And the emerging technologies might finally give us the best of all worlds. Clean power with the range and flexibility that American railroads need. The locomotives crossing this country right now are carrying the weight of an entire economy. And the next generation of machines being developed in labs and factories today will determine what that looks like for the next 100 years.